Good morning, everyone. My name is Salvatore Corvaglia, computer engineer graduated at the University of Salento and currently doing an internship at ST Microelectronics. Today I'm going to present the work I have performed in collaboration with the University of Salento, ST Microelectronics, and the other adults that described in the paper entitled Blockchain Technology Based on Algorand Applied to Low Power and Low Cost IoT Devices. This work discusses the integration of distributed ledger technology and IoT systems with a specific focus on low-power devices enhanced through the capabilities of the Algorand blockchain. Therefore, as summarized by the roadmap report in this slide, a detailed analysis was done on the Algorand ecosystem and a general research on the state of the art concerning the analysis and the performance of low-power devices based on the blockchain and the correlation with IoT technology. Subsequently, low-power devices were configured to function as an Algorand nodes, and some transactions were added to the distributed ledger. Then some tests were performed and a performance analysis was carried out on the two selected devices to understand which of the tested low-power devices better performs during the execution of the fundamental functions of the Algorand ecosystem. Finally, some consideration could conclude the paper and present some ideas that could inspire possible future project. One of the major challenge phases in the exploitation of IoT functionalities regards the need of protecting information at all levels. To this aim, in recent years, the distributed ledger technologies and blockchain are gaining momentum as solutions in such scenarios. For the purpose of this work, Algorand was selected, a self-sustaining, decentralized, secure, and scalable blockchain-based network that provide a common platform for a bird economy. Founded by Silvio Micali, MIT professor and Turing Prize winner in 2017, it is able to execute fast transactions, negligible hardware and energy costs, and very low commissions. It uses a decentralized Byzantine settlement protocol that leverages a consensus algorithm called pure proof of stake. The main goal of this work regards the integration of the Algorand technology on low-power IoT devices, demonstrating through design and performance experiments that it is possible to exploit Algorand on two of the most common low-power IoT devices without any modification in hardware or software. The selected devices are the Raspberry Pi 4 Model B with the Raspberry Pi OS Buster 32-bit release, and the ST Microelectronics STM32MP157ADK1 with the STM32 OpenST Linux distribution software. One of the main challenges in integrating the blockchain and IoT regards the processing capabilities of end devices. In fact, end IoT devices are low-power devices and can incur in problems mainly related to slow processing and small storage availability. Therefore, some existing works have already analyzed the applicability of some of the most spread blockchains on low-power devices. Algorand is one of the blockchains that is growing the most in the last years, but to the best of no knowledge, no existing work have already analyzed its applicability to low-power devices. For this reason, the state of the art of our work has been divided into two different categories. At first, the works proposing solutions to apply blockchain to low-power IoT devices are presented. Then, the works that already exploited Algorand in innovative proposals are reported. The analysis report in the paper mainly highlighted that a good and effective blockchain needs to be adapted to enable rapid transactions processing and coordination between billions of connected devices, as the number of devices worldwide is expected to nearly triple from 9 billion in 2020 to over 25 billion in 2030. To understand if the Algorand blockchain can be exploited on a device, it is necessary to verify the fulfillment of the following execution steps. Run an Algorand node to let it be synchronized with the network. When an Algorand node is run, the catch-up phase is used to process and verify each block in the blockchain, even if they are not all locally stored, thereby checking the validity of the chain. This operation is the most resource-consuming operation of the Algorand, and the monitoring of such activity can provide a valid overview of if the Algorand blockchain can be applied on a device. In addition, a new feature called Fast Catch-up has been introduced to facilitate the execution on low-power devices. Perform write and read operations through the no-run node. The blockchain is designed to be an append-only structure. Therefore, it is possible to only add more data in the form of additional block, and as a consequence, all previous data are permanently stored. Therefore, as a summary, with the aim of demonstrating the applicability of the Algorand blockchain on existing low-power IoT devices, a non-relay, non-archival node operating on the testnet was installed on the two selected devices. This type of node has been installed on both devices, that is, does not store the entire register, but only a limited number of blocks locally, approximately up to the last 1000 blocks. The configuration topology we used for the experiment is reported in this figure, where a notebook is used for remote work and devices that are connected via Ethernet cable to the modem router network ports. A local connection with a nominal bandwidth of 20 megabits per second in download and 1 bits per second in upload has been used. Finally, a Java library called Algo SDK was used to communicate and interact with the network. For the performance monitoring, the net data tool was used, and as suggested by the official documentation, the following parameters related to the CPU usage were selected for the monitoring, together with the consumed bandwidth. System, user, U8, and software. The node synchronization performances can vary depending on different factors like the number of accounts, number of blocks, technical specifications of devices, and the network. For this reason, only the most power-supplying operations were monitored with this paper, and here we report the obtained results, that is, of the transactions using the node installed on the STM32 board. On the left, we can see a transaction confirmed and written in the blockchain in less than 5 seconds, as the blocks on the Algorand are confirmed in a few seconds. On the right, we have an atomic transfer, which is an operation that allows you to send groups of transactions at the same time. The result of the grouping is that each transaction is assigned a unique group ID, and again, the transaction there was done in seconds. Here, on the other hand, two other operations were carried out, always using the node installed on the STM32 devices. On the left, we can see the creation of ASA, an Algorand standard asset, representing any type of asset on the Algorand blockchain. On the right, instead, we have an online registration transaction, as if you want to participate in the Algorand consensus protocol, you need to generate a valid participation key by registering that key online. Here we have a general table of the performance analysis of the two devices in the two most important phases, namely through synchronization of the node to the current block and the synchronized node. This is because a node can also be executed without using a feature for SketchUp, which quickly updates the node using snapshot catch points. Also, as an Algorand, a block is created every about 4 or 5 seconds. In conclusion, the experiment results show that the two devices are suitable for joining the network and able to publish transactions on the blockchain Algorand in a few seconds and perform some of its functions. Although all the operations performed successfully demonstrate the applicability of Algorand to boards such as the STM32, some functionalities are still under development. Consequently, future work could concern future experiments to further analyze particular mechanisms and new proposals. Some future work could be the following: a comparison of various blockchains on low-power IoT devices, development of a C library for Algorand to be used on low-cost constrained devices based on MCU microcontrollers such as STM32, Cortex-M architecture by ST Electronics, implementation of a use case using a smart contract, and further performance analysis on Algorand mainnets network. I would like to thank you, all of you, for the attention, and we invite you to send us any question. Thank you so much.